So we can probably move on to the next speaker, who is Chunjing Jia. She's a staff scientist at SLAC and is with the Stanford Institute for Materials and Energy Sciences, as well as the Theory Institute for Materials and Energy Spectroscopies. And she's going to be talking about WebXRS, which is a web portal for doing X-ray spectroscopies.
Thanks, Josh, for the introduction. Can you guys see the slides?
Yeah.
Okay. Yeah.
You could go to full screen if you want to. It's up to you.
Let's see. Does it work?
No, but I think it's probably fine. It's large anyway. You can see it.
Is it full screen now, or is still the same?
It's still the same.
Screen.
Oh. Let's see. I can try to.
Try that display option if you see it. That's what I did.
Oh, okay. And then if I share screen now. Is that good now?
It's full screen. That looks good.
Okay, good.
Thank you.
Yeah. Yeah, good afternoon, everyone. Today, hands-on demo of the WebXRS and other time-swap tools. Okay. Okay. So we are a Theory Institute for Materials Energy Spectroscopy, or TIMES. So we work on developing state-of-the-art algorithms to solve theory of spectroscopies with the goal of understanding and controlling both equilibrium and non-equilibrium phenomena and emergent dynamics of strongly correlated systems. So we closely collaborate with LCLS and SSRL to understand various of X-ray spectroscopy. We also utilize the superconducting cluster, supercomputing cluster, such as NERSC to perform massively parallel numerical simulations. Our theoretical approach also includes developing workflows and software, like user-friendly software that can be used to apply to spectroscopy calculations. So today my topic discussion will be basically focused on XAS and RIGS simulations. So RIGS, resonant inelastic X-ray scattering, turns out to be effective techniques for strongly correlated material studies and various other materials, energy materials in general. And in those materials, they're often intertwining degrees of freedom in the low energy regime, such as in this schematic plots, you can see that there are the charge orders, like the charge density wave here, and orbital orders, and spin. This is a spin wave, for example, and lattice is different. For example, this is lattice distortions here. So these are different orders or degrees of freedom often intertwine with each other, meaning that energy scales are very close to each other, and there are interactions between them. So like the traditional methods, usually it's pretty difficult to separate those degrees of freedom. So in this case, RIGS provides a unique tool to probe this intertwining orders in strongly correlated systems. Since there are lots of factors that you can tune in RIGS measurements, such as you can tune the absorption edge, you can tune the incoming energy to be the absorption edge of specific elements. And also you can tune the incoming energy to be within a certain absorption edge to tune to the specific valence. And also you can get momentum resolved to get the momentum dispersion of elementary excitations and by tuning the polarization of the incoming and outgoing photons, you can get access to, for example, either charge or magnetic excitations. So, so this plot shows a example of Riggs map. This is a two-dimensional false color plot. So, the y-axis shows the excitation energy or incoming energy, and the x-axis shows the energy transfer. I believe this is a one-dimensional coupled materials. So one can see that there are the spin excitation, which is located at a few hundred million electron volts, and there are orbital excitations, which are the DD excitations located around 1.523 eV, and there are high energy charge transfer, which is the charge transfer to the oxygen ligand. It has this the fluorescence features. So, so to understand the theoretical spectroscopy of this material, one usually requires like state-of-the-art, usually numerical simulations for clusters to address the different degrees of freedom, including charge orbitals, which is a pretty challenging task. But in today's study, in today's talk, I'm going to focus on a simplified version of the theoretical spectroscopy we call WebXRS. So this is a tool that mainly Tom Devereux has developed. He has wrote the code and to calculate the XAS and Riggs spectrum for simple problem. So for simple problem, we mean that atomic problem is crystal fields. So I'd like to mention that this is not designed for a very complicated system that, for example, involves the multiple degrees of freedom, like I mentioned before, for real materials. This is mainly for educational purpose. For example, if you want to learn the theory of spectroscopy for transition metal compounds, or you want to get some experience on the simple atomic calculations, or maybe you are experimentalist, you want to run some very quick test on some problems to make sure that what you have done makes sense. So these are the right tools for you to use. I want to point out that there have been various other softwares available there that you can download and run some simulations for spectroscopies. But those other tools usually involve this, like downloading and installing, which is not easy, or maybe you have to learn a different programming language, or at least you need to have some background on like maybe Python or some other programming language to begin with. So our tool here is pretty simple to use. You don't need to know any programming language. You don't need to download anything. You can just fill in the parameters, values on this on the website, and then the simulation will be run on the back-ended server, and then you can download the data, output data, and then make the plots very easily. Okay, so before I show you the demos, let me discuss about the theory, the quantum physics and quantum chemistry for the theory of spectroscopies. Oh, by the way, this is a map showing all the users from the different countries in the world. This website has only been up for about a month. You can see that we already tracked lots of users from everywhere. Well, almost a lot of different places around the world. Okay, so a schematic plot for Riggs process. So we will focus on this transition metal LH Riggs or the direct Riggs process. Or 2p 3D Riggs. So in this Riggs process, you have the incoming photon, which shoots an core electron up to the valence. So now you have n+1 electron in the valence. And then after a while, the other electron from the valence decays back and recombine with the core level to emit the outgoing photon. So we call it direct process because the core electron is directly excited up to the valence. Okay, so let me talk about the Hamiltonians in this system. So one of the main part of the Hamiltonian is the Coulomb interaction, since we are dealing with the atomic physics here. So the Coulomb interaction Hamiltonian has this 1/r term and the charge density operator n. So you can express this n with the state operator, and we have to choose a basis set A here to expand this state operator, and the C represents the annihilation operator. So in principle, one can choose any basis set as long as it forms a complete basis set, such as plane wave, atomic orbitals, or one-year orbitals. Any complete basis set should work here. And then you're going to develop this matrix element here for the Coulomb interaction term. And so to make our life easier for the atomic problem, we are going to use the spherical harmonics as the complete basis sets, and to use this well-known multiple expansion to treat the 1/r term in the Coulomb interaction. So you can express this as two spherical harmonics here. Okay, and then to substitute these basis sets and 1/r into this matrix elements, so you end up with actually 6 spherical harmonics in the integral, and for each r and r prime, you will have 3 spherical harmonics. So we express those integrals as the Gauss coefficients, which has an integral of 3 spherical harmonics. To make this coefficients be non-zero, one has to let the L and M's to obey certain conservation. Okay, then you can express this matrix element in this, and then this R of K and superscript K is the integral of the radial part. And so one usually see this thing called Slater-Condon parameters, which is the Fk and Gk, which are the density part of the correlation of R of K, and the exchange part of the RK. There is the superscript or subscript for F and G's, and there are this simple relation between the two. And sometimes one can see people use Rockoff parameters, which has a 1-to-1 correspondence between the Slater-Condon parameters. So these are the parameters we will put in for the atomic calculations. And other terms that are in the Hamiltonian includes the spin-orbit coupling. So this is pretty straightforward. It just has this L dot S and has this one parameter lambda. So the larger lambda is, the larger the spin-orbit coupling is. And then there is this extra crystal field term, so which is a bilinear in creation annihilation operators. And then this crystal field V of R, we can understand this just with similarly as the Coulomb interaction in the atomic level, but this is the Coulomb interaction between the atomic orbitals and the nearby ligands charge. So we can express this with a similar formula, and then you can expand the 1/r term. You can make some expansion, and then eventually you will use the Gauss coefficients again, and then you express this matrix element of the crystal field with Gauss coefficients and this energy, which is the integral of the radial parts. So for an equivalent way to express this is a simplified, a very simplified version is if you just know the shifted energy level or the onset energy of each the orbitals, you can express this matrix element using those values. This is pretty straightforward. Okay, so now we finish the Hamiltonian part. Let's talk about the cross-section. The cross-section is Kramers-Heisenberg formula, which is this 4-particle process. Have the ground state, have the dipole, which excites a core electron up to the valence, and then you have the matrix element of this dipole transition. Then you have this intermediate states propagator, and then the dipole, the Hermitian conjugate dipole. And for the atomic problem, we don't need to care about Q. So if you evaluate this cross section, you get Riggs cross section. Okay. So let's see. Let me show you the. How can I? Can you see my web browser for this? No.
Yes. Yeah, we can see your web browser.
You can see now?
Yeah, we can see
Okay.
it.
Yeah, sure. So this is this WebXRS website. So you see this homepage, and then let's get started for the demo. So first you set parameters. So you see this page, you need to fill out these parameters. So firstly, this code is written in whole language, meaning that you have one number of holes, which means that you have 9 3D electrons. In total, you will have 10 3D electrons, right? Then you have one hole, then 10 minus 1 equals to 9. And then the second parameter is this core spin orbit coupling, which right now we set it to be 10.5 eV, which is a reasonable number. And then those are the polarization of the inside light and the scatter light. We just keep the default value for now. And then this section is the 3D Coulomb interaction, the F0, F2, F4, the Slater quantum parameters. And the F0s are the multiple terms or the U. So we have the next section is the crystal field. The dx squared minus y squared is set to be 0, and all the other orbitals have high energy. So for this case, if we work on the whole language, the whole will prefer to stay on the lowest energy state, which is dx squared minus y squared. So think about, say, cuprates, where you have 3D 9 electrons and you have one hole located at the dx squared minus y squared. So just to get this very simple, oversimplified version of the energy diagram, you will have the correct electronic structure having just one hole at dx squared minus y squared. And then the last section is the core hole interaction between the 2p and 3d. And this F0 are the core hole. The main part of this is the core hole interaction. And then the higher order terms, F2, G1, G3. Okay, so we can submit. So now you generate input files. You click calculate. Then this is the created input file from the previous parameter setting stage, and then you submit. Okay. So now you can show outputs. The simulation is finished, and you see those outputs. It's pretty much self-explanatory. If you want to get more information, you can read carefully, or if you have a question, you can just send us emails and show outputs. So this is plots. Okay, so here you have a plotting of the X-ray absorption. So you see L2, L3 edges of the XAS. Because we don't have any hybridization with the oxygen ligands or other ligands, so you don't see a high energy shoulder. But the main feature of the atomic part of the calculation is here. We can also plot Riggs, which takes longer since the data is 2 dimensions and it's a little bit more time consuming. But let's see how well it works. Oh, okay. Interesting. It seems like the server is run with a probably high traffic. Try that again. Oh yeah, I want to point out that so far the server hasn't been designed to handle multiple tasks at the same time. So maybe that's why when more than one people run the calculation, then the server got sort of crashed. Anyway, so you can download the data files and do more analysis later. Okay, yeah, you'll see the files being downloaded. And probably running out of time, so there's another thing that I want to briefly show you, which is a slightly different one. This is www.times.stanford.edu. This is the WebXRS. So basically, it can calculate the RPAS matrix elements in the band structure. So it's just very simple tight banding model calculations. There's no interactions involved here. You just need to type in the energy, instant energy, the lattice constants, all the onset energies, and several other ligands parameters, and then you can produce some useful information for your RPAS analysis. Okay, that's all I want to talk for today. Yeah, thank you for your attention.
All right, thank you very much, Chenjing. Does anyone have any questions? I think there was an earlier question that Riti had about where you get the F and G parameters. And Tom answered some of that, but I was wondering how you normally get your F and G parameters.
Oh yeah, so those are there are, for the atomic values, there are already a lot of references you can just look up to. I will recommend that you can try with the atomic values. And then for some problem with very strong hybridization, you can get a screening factor on the monopole term, since the screening happens most strongly on the monopole interaction, like F-zeros, for example. The higher monopole terms, the high order terms you can try a little bit screening, but not usually at very small amounts.
I see.
Should be enough. Oh, Tom said there are maybe 20 people running the application.
Yeah.
Yeah, maybe confused.
Yeah, I don't. Yeah. Okay. Well, unless there are other questions, if anybody had another question, go ahead and put it in the chat. We can always answer. Oh, it looks like it gave the RIX file now. Okay. Anyway, so if people want to put things in the chat, yeah, we can always answer it afterwards. But if you have a question now, go ahead and speak up.
Yeah, the plotting worked fine before the talk. I just tested before the talk. It worked fine.
I see. Yeah, it's just too many people. So there is a question. Does this apply to gas phase XAS, for example?
Oh, gas phase. So this.
I assume that means gas phase of the atom in question. So yeah. You would be interested in neutral atoms, or maybe they'd be ionized. I don't know.
I think the current WebXRS is designed for transition metal 3D systems. I suppose for gas phase, the material may be different.
I guess if it was gas phase, truly a gas phase metal.
Oh, truly gas phase metal, then that should work. If it's a transition metal, if it's 3D systems,
That's sort of this would be ideal for that case, right?
Yeah, right. Ideal. You don't need to worry about the hybridization that much. You just work on a strictly atomic system. Yeah, that the gas phase of the 3D system will be the ideal case for this application.
But this can be useful for a lot of systems, right? I mean, I'm not that familiar with using this, but you know, a lot of the time the surroundings just change the parameters a little bit, correct?
Yeah. For example, if you like couplates or ironic tides or any like energy materials, for example, there are like different things you want to look at, like charge transfers or magnetic excitations, for example. But atomic part, like the DD excitation, the atomic part of the problem. So for that, you can use these tools. So as long as you know what you are doing, then you can focus on the part of the question that can be solved with this tool.
Right.
If I could make a comment, I don't know if you can hear me or not.
Yes.
Yeah.
Okay, good. Yeah, this is Tom Devereaux. Sorry. Oh no, my video is not on. So hold on, let me turn that on. Actually, you know, for those of you who are playing around with that, please feel, since this is an expert community, please feel free to contact me or Chenjing or Josh or any of the organizers, and you know, send us the type of features you would like to see. This is meant to be not a static application. So if you do want to have some interface where you can use a different set of software, you have some constraints on the input parameters and so on, then please feel free to let any of us know.
Yeah, and that goes for any of the talks that we're giving here, I think, as well. Okay, so unless I think